the time I think we should start. I'm happy and very much honored to introduce the speaker of today in our lecture series, Sustainability in Computer Science. It's Philipp Gschwandtner, who is well known for his work in HPC as a high performance computing. And when I read green HPC, it almost sounds like an idiosyncrasy. I don't know that as that it's kind of conflicting, these two
Yeah.
terms. But on the other hand, I think it's one of the hottest topic, especially since we have this hype of training large language models. It was just I would say a couple of days ago that Microsoft announced, all this unbelievable, 80 billion investment in building new data centers. And kind of a breadcrumb of 10 billion will go to the EU, and at least half goes in the United States.
Yes.
It's everything crazy. And Philip, I'm looking forward to your presentation, which will be as crazy, but perhaps more evidence-based than just announcements. So it's your floor. Thank
Yeah,
you.
thank you very much. So, AI and training large language models is not specifically part of my talk, but yes, this is a huge problem. Essentially, you could consider just like green HPC, only much worse than we're basically at the stage of AI. And there's been a recent study that's shown that if we continue down the road that we currently are with AI and LLMs and so on, then a large portion of the overall energy production of the entire planet will just go into these AI methods, which is like the study that I read specifically stated something like 4%. I've seen keynote speakers mention even higher percentages than that. It's really crazy. And this is also the reason for today's topic, because these things are very compute intensive. They're not going to disappear. We will have to live with them as a society, and we will need to address the energy consumption and the resource requirements. And so that's today's topic, green HPC, paving the way for sustainable supercomputing, which is a bit, sensational. But as you will come to see, it is a really large topic because these things are simply that power hungry. So first of all, what is green HPC? First of all, HPC, high performance computing. High performance computing, if you look it up on Wikipedia, it basically just says uses supercomputers and computer clusters to solve advanced computation problems. And very often when I talk to users or companies, they say, yeah, I'm not doing HPC because I'm not working on very large machines that fill entire rooms. But personally, I view everything as HPC, where I'm not only concerned with what I am doing, but how I'm doing it in terms of software. So everything that needs to run particularly fast, where you need to spend considerable amount of effort in optimizing performance, optimizing speed, optimizing energy consumption, whatever resource usage you have, I consider high performance computing, even if it just concerns my laptop or my cell phone, for example. And on the other side, we have the green aspect, obviously, which means it should happen somehow environmentally friendly. And just like this entire lecture series, there are two parts to it. First of all, there's the greenness in HPC, and there's HPC for greenness. So I have two images showing this. On the left here, you see a photograph taken back in 2010. Some of us still remember the Deepwater Horizon oil spill in the Gulf of Mexico, which was a huge environmental disaster. And we participated in a research project together with IBM and a couple of other partners in modeling and simulating how basically the oil propagates on the ocean surface, which is done through HPC. You need a lot of computational resources in order to compute how the waves behave, how the wind behaves, and so on and so on. And the other thing is a plant growing out of a PCB, which I found in an HPC Wire article, and I found extremely hilarious and silly, and I of course had to include it in my slides. But I will get to those two sides later. And yeah, the images on the right I didn't explain. So those are just visualizations of what we do today with HPC. On the left, you see the nose landing gear of a Boeing 777 and the air turbulence created by it. These have very strict tolerances in how much air resistance they are allowed to cause, how much they should cause, and so on. And it's not sustainable to test, I don't know, 1,000 different ideas of how to build these landing gears. Most of them you simply model in HPC using computational models, using scientific computing, and only the very best ideas you actually then test on airplanes, obviously, which is much more sustainable. And on the right, that's an astrophysics simulation of solar particles getting deflected by the Earth's magnetic field, which is a little bit less about sustainability, but still something that needs a lot of yeah, computational requirements and still fits the general HPC setting. So the main sustainability concern in HPC really is energy. There's a couple of others, but energy is the big player here, the big component. But why is this actually the case? Well, if we take as an example the fastest system worldwide that we currently have available, it's El Capitan in Livermore in California. And it really offers extreme computing and storage capabilities. It sports 11 million cores, even though one has to be careful because they're simply summing up both CPU cores and GPU cores. I think it's 1 million CPU cores and about 10 million GPU cores, but in any sense, it's still a lot. Over 5 petabytes of main memory. I think just over 1 exabyte of storage, but I only found articles where they said like 4 or 5 years ago how much is planned. I didn't find any current numbers of how much is actually installed, but regardless, it's still a lot. And the measured peak performance is 1.7 exaflops, which means more than 10 to the power of 18 arithmetic operations per second, which is huge. That's the upside of it. That's the good part. On the right side, you see a nice image. That's what the racks look like with all the computers inside. El Capitan is also the name of this mountain, so they have a really nice panoramic image here. What this nicely hides is the electrical requirements, because the system under full load draws almost 30 megawatts of power. And this is a problem because the main limiting design factor when building these systems is how much electricity we can pump into the system and how much heat we can get out of the system or can pump out of the system. It's not about the building sizes. It's not about the economic costs. These things are really expensive. El Capitan with this running infrastructure easily costs something like 500 million euros together with all the other systems. But this actually can be managed. The real design limitation is how much energy can go in and how much energy can go out in the transformed form of heat. Now, 30 megawatts of power sounds like a strange number. What does that actually mean? Well, 30 megawatts means we can power 100% of an El Capitan supercomputer if we have one available. I just explained that. But what else could we power? We can power only 78%, funnily, of the Aurora supercomputer, which is currently number 3 worldwide, simply because it's less power efficient than the fastest system. It also means we could power 41% of Innsbruck and its surrounding villages. So that means if we build 2 El Capitan systems, they almost have the same power draw as city with 120 or 130,000 inhabitants, which really shows the impact of these systems. So you could easily provide electrical infrastructure to more than 100,000 people, or you can use the same power to provide energy to 20 million cores or 22 million cores. Which one are you going to go for? So this is something that needs to be justified, and you can't just have power expenditures that are unnecessary. And 2 additional comparable numbers that I found due to COVID and the rise in energy prices. 30 megawatts is 9 times the average power draw of the University of Innsbruck and 4.5 times the average power draw of the University of Vienna, which apparently needs more than University of Innsbruck, but then again, it's also a larger university. And most of the power going in here is, I think, due to lab equipment, and actually only a limited amount is really due to office space and lighting and so on. But it's still extreme, showing that this one HPC system beats both universities combined, which really shows you, how much resource power needs to go into these things. Now, what we want to do is we want to optimize that. We want to try to reduce the energy draw and the power draw and make them as sustainable and make the systems as little power hungry as possible. But we cannot optimize something that we cannot measure, so we need to measure first. And there's really a plethora of research being done in this topic, both on the measurement side and on the modeling side. So whatever you do, you need some kind of power or energy data. One choice is to do experimental platforms and use experimental devices. I have some photographs here on the right with some industrial grade power meters, like this Voltec device, for example, or some devices that you can actually find the blueprints online and simply solder yourself together if you know how to use soldering iron. There's a couple of problems though. Besides the research aspects of how accurate these devices are, what the resolution is, and so on, these approaches don't really scale because if you want to know the power draw of your entire HPC system with millions of cores, you need a couple of thousand of those devices. This doesn't really scale, especially for the devices that you have to build yourself in the first place. Also, for those of you who are interested in doing, hobby research work into these topics, you have to be really careful, especially with these devices that you build yourself. Because I remember attending a conference or a workshop a couple of years ago in Hamburg, where a PhD student presented their experiments on energy optimization, and they said the first time they assembled one of these devices and attached it to the main board actually went up in flames, and they had to order another one from the vendor. And these things really can be a fire hazard. So you have to be careful about that. And anyway, for larger supercomputers these days, thankfully, it's no longer an issue because modern supercomputers have this built in already. Some of them do measurements, some of them do quite clever and sophisticated modeling. I'm personally not a fan of models because models often depend on tunable parameters. They depend on accurate and representative training sets and training data. If your productive workload differs too much from that, then the model might no longer be accurate. And how are you going to know? So I'm personally always a fan of getting actual measurements because measurements for me depends on physics, and physics is rarely wrong. But still, there's a lot of work also being done here. You just have to know what you're dealing with. Once we have the data, we need to establish some kind of metrics in order to be able to, digest this data and use it for our optimizations, to drive our optimizations. And there's a lot of metrics out there. I'm only going to present two examples here because it would be too much even for the entire lecture. One of them is power usage effectiveness, or PUE, which is basically an indicator of how efficient a data center or a supercomputing center is. It's simply the fraction of the total facility energy divided by the IT equipment energy, which means how much energy does the entire building consume with all the cooling infrastructure, all the lights and so on, compared to the power you need for only operating the actual IT equipment that you want to power. Ideally speaking, the PUE is 1. We are usually never going to reach that because you always have some kind of overhead. But these days we are in the 1.0 something realm, which is quite efficient. And 30, 40 years ago, you would have power usage effectiveness of 2, for example, which means half of the energy was spent for cooling a system and only half of the energy for operating the system, which was really, really bad. This metric is more interesting to the operators, actually. For the users, we usually look at something like EDP, the energy delay product, which means, okay, you want to know how efficient your program, your application is when you execute it, but not only in terms of time, but also in terms of energy. So you simply multiply the wall time, so the time your program takes to run, with the energy it consumed, and you arrive at the EDP. And there's a couple of variants where you can put weights on energy by multiplying energy times wall time and so on, or energy times wall time. Really depends on your actual objective. But that's just, yeah, two examples of how to work with this data in the end. Once we have this data, one thing we can do is compile nice lists and do competition worldwide, which is what people and institutions do in the top 500 list. So the top 500 list is a list of the fastest supercomputers worldwide. Some of you might know it already. Released twice a year. And essentially what they do is whenever they build a new system, they run a lot of heavy linear algebra, like matrix multiplication, matrix multiplication, linear decomposition, and all of these things to get the performance of the system. And then they rank their systems worldwide to see how fast they are. Here I have the fastest 5 systems. I don't know if this is readable through the video stream, but the actual numbers are not that important. The important thing is that sustainability is really here nowadays because besides the rank, the name of the system, the number of cores, and the performance, one of the main columns of this data is the power draw when the system was benchmarked, when the system computed these performance numbers using linear algebra. And you see, not all the systems have these power numbers. So to be in the top 500, you don't necessarily have to provide these numbers. But it's basically, good reputation if you do. And all the larger systems basically do it these days, almost all the systems. Besides the top 500, there's also the green 500 list. And the green 500 list is not so much about performance, but it's really about energy efficiency. So for the top 500, in order to appear in the first place, you need to have the fastest system. For the green 500 to be at rank 1, you need to have the system that is most energy efficient. And they compute it as the number of arithmetic operations per watt spent on these computations. And you can really see that these are two different goals because the system ranking first place in the green 500 only ranks 222nd place in the top 500 that ranks according to performance. So there's a vast difference, and there's over 200 systems faster than this system, but none of them are more energy efficient, which really shows this trade-off. And the Green 500 is a really tricky ranking or a tricky list because there's a very concise, very elaborate at the same time specification on how to do these kind of measurements in order to be in that Green 500, and it's 33 pages long of defining measurement devices, defining topologies, measurement topologies, infrastructures, network, defining workload requirements. What's the minimum duration for how long your program needs to run? How much of your application do you need to measure? Do you only measure the computational core, or do you measure everything, including reading input data and writing output data, for example? There's a huge section on statistical means, like averaging through the arithmetic mean, the geometric mean, the harmonic mean, depending on what metric you're dealing with, depending on what data you're dealing with. I'm not going to go into detail for any of those. Just one of the most important things when you look at the Green 500, at some point you will arrive at the information at what level something was measured. And there's basically 3 levels of increasing accuracy. Level 1 only requires you to measure, for example, the core phase of an application, requires you to measure a subset of your supercomputer, and you're allowed to extrapolate to the entire application and to the entire system, even though you only measure the part of it. And if you have some components for which you don't have the energy specs or anything, you can simply, or I don't have the energy measurements, sorry, you can simply get the information from specification and data sheets. And then level 2 is a little bit more accurate, where you have to measure more, up to level 3, where you have to measure the entire application and you have to measure the entire hardware that was, employed for doing these performance measurements. And you have specific requirements on the resolution and frequency for direct current measurements, for alternating current measurements, and so on and so on. And these are really difficult to achieve because you need to cover the entire system. So they really take it seriously, and it really arrived. And the Green 500 list has been maintained for years already. That's not something that just appeared yesterday. Now, what can we do with this data? One of the interesting things is we can do a projection of the power consumption, how to reach 1 exaflop. So you see 2 lines here, the blue or turquoise line, that's the fastest system in the top 500, and the red line is the fastest, or the rank number 1 in the Green 500. And for each of those systems, we extrapolate how many megawatts would it take using linear scaling in order to arrive at the performance of 1 exaflop. And from 2008 down to 2021, 2022, you can see this has been ever decreasing, which is a good thing because that means our systems get more and more energy efficient. Every year, or almost every year, we get systems that are more energy efficient and would require less megawatts in order to arrive at the performance of 1 exaflop. These days, at 2024, 2025, we already reached 1 exaflop, not necessarily at this magical line of 20 megawatts, which is sort of a psychological limit of us considering it to be quite energy efficient or quite good at, making use of the electrical power put into it. Originally, back in the 90s, this was envisioned as the limit, and we couldn't build any larger systems. But yeah, now with El Capitan consuming 30 megawatts and Aurora 38 megawatts, has already been thrown out of the window. But still, it's a very good psychological line and aim for us to try to be more energy efficient. Now, once we have this data, what can we optimize? Well, there are several avenues of optimization that we can take. First of all, to make HPC more energy efficient, we can try to increase the parallelism. I have a slide on that later that shows history and the historic overview, how we got there in the first place. We can try to make also cooling more efficient because cooling infrastructure plays a really large role because of all the heat. Remember, all the electricity that goes into the system, sometimes or I often call this energy consumption and power consumption. Energy is never consumed, right? Physicists will basically roll with their eyes if I say that. Energy is always transformed from one form to another. So electrical energy is transformed into heat, and this heat needs to be dissipated somehow. So cooling is a major, major requirement doing this properly. And obviously, you can also select what hardware you use and how you use it. I will also get to that later. And when we work with HPC, it's usually always a multi-objective problem as soon as we consider energy, because whatever is most energy efficient is probably not the fastest solution. There's usually always a trade-off that's to be managed. And that gets us into the realm of multi-objective optimization and optimization approaches like Pareto optimality, which some of you might know from other domain sciences. For those of you who don't know, I have an illustration here on the right where we have one objective, time, on the x-axis conflicting with another objective like energy. And whatever your optimization space is, say you have a program with a couple of tunable parameters, you have a couple of different hardware systems available, at some point you will arrive in the situation that you have two different selections, but none of them beats the other in all objectives. One is better in one objective, the other one is better in another objective, and you need to choose, you need to prioritize. And then we have this entire realm of mathematical optimization approaches for multi-objective problems, which also applies to HPC. And you need to have the data center operator decide, okay, today I'm going to slow down my system because it's hot outside, for example, or users choosing between energy optimality and performance optimality. Now, I mentioned the historic overview, and this is the single slide I have on this. I think it's quite important to know or to see in the historic data how we got into HPC and parallel computing in the first place. What you see here is trend data from microprocessors from the 1970s to today. And each column of markers here represents one chip, one architecture that was, common at the time. And each of those points for this one chip denotes the number of transistors, how fast it was in terms of single speed performance, what's the clock frequency, the power consumption, typical power consumption, and also the number of logical cores. And what we see throughout the decades up until 2005, we stuck to a single core CPU and we simply cranked up the operating frequency, which was easy to do and was also very nice for the users because back in the 90s, if you wanted a faster system, you only needed money. If you spend money on a computer that's twice as fast, your program will run twice as fast, at least roughly speaking. But around 2005, you see this frequency curve flattening off. And at the same time, also the typical power consumption sort of flattening off because that was the limiting factor. We cannot build devices that dissipate 1,000 watts in a couple of square centimeters because it simply doesn't work. We cannot dissipate the heat fast enough. So as an alternative, instead of clocking up our systems faster, we started to increase, or the CPU designers and developers build CPUs with larger numbers of cores and increase the parallelism because that's cheaper compared to increasing the frequency. The number of transistors still grows, but now it's not put into making systems faster and making systems more complicated, but simply adding numbers of cores, which is where we arrive today. If you work on modern server hardware, you easily can find CPUs with 64 or 96 cores, for example. The downside is for us developers, we now need to write parallel programs. Back in the 90s, we got additional performance for free, as in, work effort. You only need money to spend on a CPU that's twice as fast. These days, with parallelism, we need to make sure that our software is written in such a way that it scales properly and it actually can make use of those resources, which is more work for us, but there's simply no way around this, unfortunately. Another thing that you can do is simply switch technology entirely and move to accelerators. If we look at the top 500 list throughout the years and compute the number of accelerated systems in the top 500, you see that this has been increasing. Not monotonically, there are some years where it went down again, but these are usually singular impacts, like here, for example, in 2015, sorry, when Intel basically stopped their Xeon Phi brand, then operators and sites that use this brand basically had to direct their efforts and switch hardware. But other than that, it's been steadily increasing. And why is that the reason? Because distributed memory clusters with accelerators simply provide some of the best energy efficiency. If we look at the top 10 in the Green 500 from 2022, for example, all of them are accelerated, and 9 of the 10 use GPUs. I don't have up-to-date data on this, but I looked at the 2024 list from November, and basically these conclusions still hold. It's basically impossible to build an energy-efficient system these days without accelerators. So this is also something where we need to be aware of this because we need to write accelerated code. We need to use CUDA, SYCL, or some of these programming models. This doesn't really come for free. Another way of looking at this is by drawing a line of 10 gigaflops per watt of energy efficiency and checking which systems in the top 10, for example, are above and below. And if we draw this line, we see that all the top 10 systems above use accelerators and all the systems below do not use accelerators. And there are only two exceptions to that. One system above this line is Fugaku, formerly the fastest system back in 2022 or so. And it was very energy efficient despite having no accelerators because it was ARM-based. It used the same technology in our smartphones as we use in our smartphones, using Fujitsu-made 48 core CPUs, I think. Very energy efficient and almost meeting the energy efficiency, for example, of Summit, which was supplied with NVIDIA V100 GPUs. But definitely not beating the more modern A100. And the only system that actually uses accelerators but is below this line is the Tianhe 2A system, which uses special kinds of accelerators, 128 core RISC CPUs that are simply special purpose built and do not fit the general purpose scheme so well. We can also draw the entire top 500 data from that time. And the figure doesn't look like it, but you really see 500 points, 500 data points in this figure, and simply group them according to what accelerator they use, whether they don't use any accelerator at all, or whether they used Xeon Phi, the NVIDIA A100, the Tesla K GPUs, which are really old by now, the V100, and so on and so on. And then we really see three major groups. We see the group of no accelerator at all, and they are very low on the gigaflops per watt scale, so on the energy efficiency scale, not reaching this magical barrier of 10 gigaflops per watt, except for 3 or so systems that are simply special purpose built. Fugaku would be one of those. And if we look at the other two clusters, we see the NVIDIA A100, which is basically the systems with the highest energy efficiency, and the NVIDIA Tesla V100, which is still more energy efficient than the systems without any GPUs, but not as energy efficient as those systems. That's simply because the V100 cards are an older generation. They're 1 or 2 years older than the A100 cards, and these systems would be now outperformed by the most modern Grace Hopper architecture, obviously. Now, what else can we do? So far, everything we mentioned relates to hardware. We can try to improve cooling, we can try to improve parallelism, but we can also work with software, and this is where tuning comes in. There's a lot of research because whenever you buy a system, you have to stick with this system for 5 to 7 years because that's roughly how much time you need to spend with the system in order to accumulate enough money to buy the next system. So during this time, a lot of research is done in software in order to make software run more efficiently on the same hardware. And that's quite interesting. I'm showing two examples of research that I did a couple of years ago in energy research. And in the top figures, you see the energy efficiency of using the GCC compiler compared to using the IBM compiler on IBM hardware, on an IBM Power 7 CPU. And what you can see here is that most of the time, GCC produces executables that are actually worse in energy efficiency. So here, for example, for this benchmark, 75% worse compared to using the IBM compiler, which is not surprising because IBM builds the compiler, IBM builds the hardware, so it should be most energy efficient. But funnily, that's not the case for some selected benchmarks. For the UA benchmark here, for example, GCC produces executables that are 30% more efficient than IBM's own compiler on IBM's own chips, which I found quite interesting. And this is a point where compiler developers should look into the topic and figure out what's going on. I hope they fixed it by now. IBM Power 7 CPU is quite dated these days. That research is from 2014 or so. But still, that doesn't mean just because you're using the same vendor compiler, it necessarily beats any third-party solution, which is quite interesting. And the figure at the bottom here shows frequency and voltage scaling and shows the energy consumption of running a benchmark on the Intel SCC, which is an experimental chip from a couple of years ago. And the interesting thing is you could run this chip at selected frequencies from 100 megahertz to 800 megahertz, but neither the fastest nor the slowest setting is the most energy efficient one, but it's somewhere in between. And which of those frequencies is the most energy efficient one, which is the sweet spot, really depends on the workload, really depends on what software you're running. So this is used heavily in supercomputers these days, especially, for example, at the SuperMUC in Munich or Garching, to be more precise, at the Leibniz Supercomputing Center, where they basically measure applications and measure how memory intensive they are, how compute intensive they are, which components of the system they stress, and then automatically select an energy optimal setting unless the user overrides that. And overall, they can save a couple of percentage points, which may not sound like a lot, but considering the size of the system, overall in absolute numbers, it's actually quite a lot. It's enough to employ a couple of researchers instead of spending, power, which is quite interesting. There's also a lot you can do in cooling these systems, and this gets us to one of my favorite stories from the past, VSC3. VSC3 is formerly the fastest supercomputer. It was the fastest supercomputer in Austria in 2014. Today we have the VSC5. And there's a couple of things, a couple of reasons why the system is not special at all. It's not special because when they built it, it ranked 85th worldwide in the top 500. There are 84 systems that were faster. It's also not special because it used almost 33,000 cores. There are many systems that were larger than that and 450 kilowatts of power draw. There are systems with less than that and there are systems with more than that. What was special and interesting for the system was the power usage effectiveness of 1.02, which is really, really efficient. Compared to the VSC2, which is the predecessor system and which was water-cooled, of 1.18, which is worse, and the successor system of 1.05, which is also worse. So what did they do with the with the VSC3, sorry? With the VSC3, they cooled it using oil. And normally, if you know what supercomputers look like, they usually look like racks with the compute nodes pushed into it, the rack like a drawer in a closet, for example. And this is not really what this looks like. This more looks like something where you open a lid on the top, it looks like a fridge or something, and there's a lot of cables running into it. The reason for that is that these are actually tanks, and these tanks are filled with oil, and the compute nodes, one of them is just sitting on top here for illustrative purposes. These compute nodes are actually submerged in the oil vertically, and only the top connections were basically outside of the oil in order to be able to connect the network, connect some serial interfaces, USB if you have, and so on and so on. And this is why this is also called immersion cooling. That means you really have immersive cooling where you have all the hardware that is producing some kind of heat in the cooling medium. Now, oil is very efficient because oil is very good at transporting the heat. They were able, because of this immersion cooling, to save on a lot of fans and pumps because you simply use convection. The components that were producing heat basically heated up the oil. Because of convection, the warmer oil rose, pulling colder oil from the bottom. You have some natural convection, which saves you pumps and having to do this manually. And you can simply transport this away, have some heat exchanger somewhere and be happy with it. So oil is very efficient. Oil is also a huge pain to work with. So you might notice that you have two white squares here on the floor. those are actually kitchen towels. And they're not here by mistake. Somebody deliberately put them there because you might notice that every now and then the floor looks a little bit more shiny because there's a lot of oil on the floor and people used to slip a lot. So there's also something here in the back, which I think is here for the same purpose. Oil has the problem that it simply creeps everywhere. You cannot get rid of it, and it also doesn't evaporate like water, for example. So once it's on the floor, it will stay on the floor until you clean the floor. That's one reason. Another reason is at some point they started to have network failures, and it was really curious because the network switches were not oil cooled. So what you have here is you have oil creeping up into the network cabling infrastructure and creeping along the network lines outside of the tank into components that were never oil cooled to begin with or never intended to be oil cooled to begin with. And those are just two stories of many more stories why this is not done anymore. It's very efficient, but it's not user friendly. And it's not very economical because components that break that were not supposed to break. So these days, people are jumping back and going back to water cooling, simply doing water cooling in the most efficient way because it's much more user friendly. An example here are two nodes of the SuperMUC NG, one of the largest systems in Munich, where you have one of these compute blades with CPUs and GPUs, the main memory modules, and so on. And you have two large connections where you have water flowing in through one connection and hot water flowing out through another connection. And these are really manufactured with very tight tolerances, trying to get the maximum out of the system. On the slide through the video stream, it's probably a little bit too small to read, but here, for example, you have one of the cooling devices for the CPU, and it first of all tells you it has 4 screws, and it tells you in what order to tighten the screws, and it also down here tells you what torque to use. So it specifically says 1.4 nanometers through 1.6 nanometers, which is the amount of force essentially. With what to tighten the screws. If it's less than that or if it's more than that, it's out of the spec and you're out of warranty, which shows you what the tolerances are in those systems because you have water flowing through this thing. You really need to adhere to the spec. And here I have a small animation showing that through this connection you have cold water coming in, cooling the main memory modules, cooling some other components like CPUs and GPUs, and then once the water is warmed up, it will flow back out through the outflow connection, and needs to be cooled then. And there are a couple of technologies or methods how to do it, which gets us to the next slide, because cooling the nodes is only one part of it. If you cool the nodes, you put cold water in, you get warm or hot water out, but now you have this temperature gradient and you need to bring the hot water down to the cold level again to be able to push it back into the nodes. And there's multiple different means of doing this. So first of all, you could try to get rid of water cooling and use air cooling alone. This is what everybody does these days. Our laptops are cooled. Many of our PCs are cooled like that. It's very inefficient because air actually is an insulator. Air doesn't transport heat that well, but it's simply easy to build and maintain, right? That's why we don't have water cooling in our laptops. If you really want to go into water cooling, there's warm and cold water cooling, and those are just different in terms of how the water is cooled down. Both of them are difficult to build and maintain because water and electricity usually don't go along very well, right? But still, if you build it, you can have warm water cooling where you simply pump the hot water up to the roof of your building, for example, and simply use the ambient air without any additional means to cool the water down. That's why it's also sometimes called free air cooling. And this makes it very efficient, but it's only suitable for cold climates. So this is something you can easily do if you build a data center in Scandinavia, for example. If you go to Southern Europe, you sometimes need to actively cool the water down. And this is where we come into cold water cooling, which is not as efficient anymore because you have active chillers on the roof of your building that work like a heat pump, that basically work like your refrigerator to actively cool your water down, which again takes electricity. It takes energy to pull this heat away from the water. And beyond that, there's also really, some, I would say, ancient solutions maybe for indirect cooling, where you cool the hardware with air and then you cool this air with water, which sounds indirect and sounds inefficient. But remember, if we look at those nodes, there are only so many components you can cool with water. There's no water flowing through any of these electrical components here in front. So you always have some limited amount of hardware that relies on air cooling, and this air needs to be cooled down again in turn. So to some degree, you always have some amount of indirect cooling probably. And on the right, you see a statistical overview of a 2020 survey among the largest supercomputing sites in Europe. The majority of them use direct warm water cooling. Why? Because it's the most energy efficient solution that we know these days, besides oil cooling, which we don't do anymore. The next one is direct cold water cooling, which is probably the next most efficient, except that we have to actively cool the water down. And all of the others, like air cooling and indirect cooling, are in the 10 or 5% share range only. So not that popular simply because they're not that efficient. What can you do with this heat energy? I have an example system here that's already a couple of years old, but back then had a really, really nice PUE of 1.06 from the National Renewable Energy Lab in the US. And it shows you the flow of energy and heat throughout the entire system. So you get cold water into your flagship HPC system that has the highest power draw and is the largest heat dissipator. Then you have hot water coming out of the system, and through a heat exchanger, what do? You actually heat office building and you heat the campus with it. That's something that every larger system has to do these days. Otherwise, you cannot operate efficiently anymore. You cannot operate sustainable anymore because nobody wants to simply dissipate heat out on the roof if you next door have office buildings that need to be heated up for people to work comfortably when it's minus 10 degrees outside. Only after heating the office buildings, the remaining heat you try to get rid of passively without active cooling through free air cooling, for example. Then the remaining temperature gradient, if there is any, you will do with active cooling. And then the cold water at the coldest level goes first into the legacy IT systems and then into the flagship systems. Most of the time, because these are more inefficient to cool, so you need much colder water flowing into the system to still cool this nicely. And yeah, then you move back to the flagship system. And on the right here, we have an overview of the energy, as in electricity, flowing into what parts of the system. So this is the flagship HPC system. Here we have legacy IT. And you see it's really really efficient because only a very small part of it moves into cooling, pumps, air conditioning. And here this is lights and electrical power outlets. And then you can see how this energy flows through the cooling technology and how it's dissipated yeah, on the roof. And this next slide basically just shows the same, how we can use this heat that we get out of the system. We have an inflow temperature here. That's an example system of IBM research. An inflow temperature of 60 degrees, an outflow temperature of 65 degrees. And then these 65 degrees or the 5-degree difference can be used to heat up some systems with appropriate measures, for example, can be used easily for underfloor heating. And underfloor heating, for those of you who know, already works if you can heat up water up to like 35 degrees or something. You really don't need a lot of temperature in order to operate floor heating. And this is something that all the larger supercomputing centers do these days because you cannot do without anymore. Now, I talked a lot about sustainability in HPC, which is the research that I did, which is the research that a lot of people did. But there's obviously the other side also, that you're using HPC for sustainability. So there's a lot of research going into how to operate wind generators, how to build them efficiently, what materials, what the shape should be, how much of the wind energy we can actually get out of the system, which is interesting because I once saw a study that about 35% is the maximum you can get out of wind energy. If you extract more than that, you slow down wind so much that it hurts your efficiency again. So 35% seems to be the peak apparently, or at least that's my state of knowledge. Or we can also run, for example, simulations of car crashes. Back in the 60s and 70s, if you build a new car, you had to deliberately destroy 50 or 100 of them in order to figure out whether they were safe to operate on the road. These days, most of the crash simulations are actually done simulating in the HPC system, which saves a lot of resources, saves a lot of metal, saves a lot of also economic costs, and also only a couple of these cars are actually built for being crashed in order to verify our simulations. So there's a lot of modeling and simulation in HPC that is done for simply making other processes we need as a society consume less resources. And you could fill an entire semester of lectures with these topics. Not going to go into more detail on that. Besides all of these things, there's also a couple of open issues, unfortunately. There's more than energy and power. We could also compute carbon usage effectiveness or water or space usage effectiveness. Didn't go into any of those, but obviously each of those has their own merit to it and might be more important than energy alone, for example. Also, if we restrict ourselves to only power and energy, there's power usage effectiveness, then there's only partial PUE if you can't measure the entire system. There's energy reuse effectiveness and energy reuse factor, which are more sophisticated than the PUE because they take into account whether you're using some of this heat in order to heat office buildings, for example, which the PUE doesn't. So the problem here is really there are way too many metrics and many of them are inaccurate. And this is a lot of marketing going on here. If you want your data center or your research to look good, you simply select among the 30 metrics the one that looks the best, that makes your research shine, which is a general problem in science, obviously, but also it's a problem here. And also some of these metrics are flawed. The PUE, for example, cannot compare HPC sites in different climate zones. If you can use free air cooling or you cannot use free air cooling, that makes your PUE look different if you choose the right PUE. If you don't, then it's the same and it's not true and it doesn't apply. And obviously, there are also diverging interests. For example, the data center operator tries to look to make their system consume as little power and energy as possible and also to maximize the workload throughput to get 100% usage out of the system. Whereas the user just wants to have the result as fast as possible. Often they don't care about the power and energy draw, especially in the scientific community, because we don't really pay for those systems, at least not ourselves. And the taxpayer and politicians, they are only interested in minimizing the costs, which sometimes is the same as minimizing power and energy, but not all the time. So more energy efficient hardware, for example, is usually more expensive because it's at the bleeding edge of research and development. Now, where can we go from here? There are a lot of future developments and ideas on how to make these systems more energy efficient. There's high bandwidth memory, for example, because data movement is actually very energy hungry, power hungry. It's really difficult in terms of power envelopes to move data long physical distances. So we literally try to put the memory chips where we store data and the compute chips where we compute this data physically as close together as possible, because actually that minimizes data transport distance and also minimizes the power draw required to do that. Many modern devices use HBM these days. We try to reduce the fabrication size, like the nanometers that you read whenever you look at the fabrication size of chips. But this means also research in new designs and new materials, because the current materials only go to around 1 or 2 nanometers. But you have to be careful because different companies and vendors use different ways of measuring this. So 1 nanometer is not the same as another nanometer for different vendors. There's the area of near threshold voltage computing, where you operate a computer below safe operating limits, below the voltage it needs to operate safely, and you take computational errors into account, which is a really interesting field of research. And there's also a lot of special purpose built hardware like accelerators, especially for AI these days, which is a huge topic, as we mentioned in the beginning, FPGAs, and also custom hardware designs for very domain specific problems. The most energy efficient solution would be to build your own chip for your problem, but that's very expensive, obviously. So there's a trade-off here. And there are, really interesting ideas like optical computing. There's some research out there in using photons instead of electrons to do computing on chip, which would be really, really efficient in terms of heat dissipation. But it's not clear yet if this is really a viable alternative. And I'm not mentioning here quantum computing, but obviously that's also an alternative approach. One really funny idea I would like to close my talk with is reversible computing and Landauer's principle, which I don't fully understand because I'm not a physicist, and this somehow for me goes into the realm of philosophy also, but I found it very interesting. I read this up in physics papers that I don't fully understand, but apparently experts on these topics agree that this is a thing. So let's have a brief introduction. Apparently, there's a lower theoretical limit to the energy consumption of computation. Why is this the case? Today, we normally have irreversible computation. Consider a logical AND operation where we combine a 1 bit with a 0 bit, and using a logical AND, this results in a 0 bit. But we destroy information here. I cannot reverse this computation because if I have a 0 here and I know this was an AND operation, either both of those bits were 0 or one of the two was 1, but I don't know which situation we initially had. If we erase information, apparently, we need to have an increase in entropy, and that means an increase in heat in a closed system because of thermodynamic laws, apparently. Now, the Landauer limit, the minimum energy consumption we can have is really low. It's 0.0175 electron volts or 10 to the power of minus 21 joules at room temperature, which is a really, really, really low number, and we are many orders of magnitude away from that. So not a problem. However, there's also something called Kumi's law, and that's similar to Moore's law. Moore's law, you might have heard, that means approximately every 2 years, our computational power of our devices doubles. It's no longer true exactly. There are lots of divergent opinions, but roughly it held for the last couple of decades. And Kumi's law is sort of similar. It says the number of computations per joule doubles every 1.6 years. But if we combine that with the Landauer limit, it means that we cannot increase energy efficiency further by 2080. By the year 2080, we would have reached a minimum amount of energy, which to dissipate by doing irreversible computation. And because this is a physical limitation, this also applies to quantum computing. What's the solution to this problem? The solution is, okay, we got into this problem in the first place because we did irreversible computation. So let's just do reversible computation. Let's develop new chips and new math that allows us to reverse each of those computations that we do. So according to physics, that would mean we wouldn't have to increase the entropy and hence have no heat dissipation. Whether this is a solution, whether this is possible, I leave to physicists and philosophers. I just find this a very, very interesting topic. So I hope I was able to give you an insight into green HPC and the problems we have with energy in HPC, and we really need to address them because the large systems consume a lot of power. But there's a lot of really interesting research going both into sustainability for HPC and sustainability with HPC. And power and heat are really the main limiting factors here because everything has to use water cooling these days. We really focus a lot of our efforts on to make this as most efficient as possible. Reuse waste heat to warm office buildings or to do something else with the heat. And the short-term developments here are quite clear. Long-term developments like quantum computing, optical computation, or even this Landauer limit stuff are still quite unclear, at least to me. If you have any questions, I'm happy to take questions now. But if you want to contact me afterwards, I just have some coordinates here. Feel free to let me know if you need further information. And yeah, thanks for listening.
Thank you, Philip. Amazing.